Okay, so um, now we'll get into that kinetic energy we were talking about, and the energy of motion. So if you have a velocity, you have kinetic energy. It could be rotational, going around a circle, or translational in a straight line. And we'll look at just the straight line kinetic energy. Um, we'll consider our energies in a straight line. Um, so it refers to energy of a particle by the virtue of its motion. And we can get to kinetic energy from the work formula, or we can get its mathematical expression from work. So we start out with work is force times delta S, right? But we could also write it in its other form, which we showed was force times V bar, times delta T, right? And a force, though, is also a mass times acceleration. So instead of F, it could be ma times V bar times delta T. But V bar is Vi plus Vf over 2, right? Well, let's take our initial to be 0, so we'll just have it as Vf over 2, okay? So when we plug that in over here, we have m times a times Vf over 2 times delta t. But of course, a is delta v over delta t. Delta v is Vf minus Vi, but we're just going to take Vi as 0, so we get Vf over delta t. So for A, we'll plug that in, Vf over delta t. So now we have m times Vf over delta t times Vf over 2 times delta t. We can see that the delta t's cancel, and we get m times Vf times Vf over 2. Getting rid of the final for the velocity, we could see that we end up with 1/2 mv squared, and that's our kinetic energy, K. So from the work formula, we can get at kinetic energy. And the kinetic energy formula is 1/2 of the mass of the object times its velocity squared. Here's an example. Compute the kinetic energy of a 60 kilogram sprinter running at 11 meters per second. K is 1/2 mv squared, and this is just a simple plug-in problem. (3,630 joules is our kinetic energy. Now we'll go right into 6.9 here, which is potential energy. And in our sense, we're going to look at gravitational potential energy. Now, gravitational potential energy is given this symbol U. Okay, we've used P for power, so we're done there. And we put a little G there for gravitational, UG. And potential energy is something that is very often poorly defined with misconceptions. Okay, potential energy and kinetic energy are not antonyms. Okay, potential energy is not the energy of a body at rest, and potential energy is not stored energy. But what potential energy is associated with position of an object, okay? So, for example, if you're up here on a bridge, or a cliff. You can have gravitational potential energy in relation to the position of the ground below. Okay? You could also have gravitational potential energy in relation to the position of the middle of, like, say, a ledge that's off here. So you could have this potential energy in relation to the ground, and you could have gravitational potential energy in relation to the position of the top of that other ledge in blue. So it depends on where you are, or it's just on location differences. If you were somewhere you don't want to be, you have potential energy in relation to the place that you do want to be. Okay? There's many different types of potential energy, electrical and chemical potential energies that stem from charges being where they don't want to be, elastic potential energy from stretching or bending or compressing something. And right now we're going to focus on gravitational potential energy, and we'll look at electrical potential energy later. So if you take simply, let's take this person here, and this person had to move up. So let's say we put him on a lift or something, and we had to move him up to do work to get him from the ground level up to there. So we'll just look in terms of relation to that ground level now. So what is the gravitational potential energy of the red person in relation to the ground level? Well, we'll start again with the work formula. But in this case, the work that's being, what work is the person, are we doing to lift them up to that position? Well, that work is the person's weight, Fg, and the delta S is the H, mg delta H, as in change of position, and that equals Ug for potential energy. So just to get them up to that position. The location of the zero potential energy, in this case the base, the ground level right here, is arbitrary. It could have been the top of the blue level as well. It depends how you're defining it for the problem you're doing. Gravitational potential can be negative if you define the tabletop as where it is and where the ball moves down something, then it has less potential energy than it did on the tabletop, so it's below zero. To return it to the tabletop, you'd have to do some work on it. When I pick up a ball, I do work on it. If I let it go, it falls back to the ground. It wants to be on the ground because gravity is pulling on it. If I push a ball along the floor, it won't spontaneously roll back to its starting point after I stop pushing it. It doesn't like one position on the floor any more than the other. This allows us to find an equal potential surface. If you can move along a path without changing your potential, you're moving along an equal potential surface. So, for example, of people in a bleacher level, okay, like so. All these people may have different masses, but they all have the same potential level, a certain energy level that they're on. And it's that level that where they are would be divided by their potential energy divided by their mass, or just G delta H. So everybody in there on that level has a G delta H, whereas everybody up here, despite their different masses, has a different G delta H. We call those potential surfaces. We'll come back up when we talk about this in electricity. Here's an example. What is the gravitational potential energy of a 70 kilogram man on a bridge 84 meters up from the ground? So the person standing on the bridge, and this distance down to the ground is 84 meters. And just simply UG is mg delta H, 70 kilograms times 10 meters per second squared times 84 meters. It's simple as that. Not all that difficult. $58,800 joules. It gets more interesting when we put these together in terms of conservation of energy problems, which we'll do next. But that ends it for this video. 8.8 and 8.9.